Well, not everyone has made it back from lunch, but we're going to get started now. So I'm delighted to introduce Miles, who in the rest of his time works on planetary models or something like that. But in today's talk is going to be talking about symbolic distillation of neural networks. Well, go for it.
Can you hear me through this one? Okay, cool. Okay, so I'm going to talk about one strategy for converting insights learned by deep neural networks into a language that we can understand. Okay, so what I want an AI scientist. Okay, I want a machine learning algorithm that will actually do science for me and help me in my scientific research. But I think a lot of existing machine learning research has been driven mostly by computer vision, natural language benchmarks. This was motivated by industry interests, robotics, attempts to reach human level performance on various tasks, and kind of you have these different benchmarks along the way, so like image classification, for example. And I think this is a problem for machine learning and science research, because I feel like a lot of machine learning science research just takes computer vision or NLP benchmarks and kind of swaps the data with scientific data sets. But I think like this is not really, this kind of misses the point. So I think machine learning plus science, we kind of need to go backwards, work backwards from we want to discover new science and kind of build up problems that support that. So I want AI to reach human level performance at doing natural science research. What needs to happen? So natural science, it's not a regression problem. It's not a classification problem. You need to have an understanding of the things the model learns. This is kind of a key difference here. We want to be able to use machine learning for discovering kind of universal concepts and representing them in human language. This is kind of the key difference. So, okay, how do we traditionally do science? So we have maybe some data set, maybe it's a low dimensional summary statistic, and we try to describe it with theory. So we come up with different theories that try to describe that data set. So for example, Kepler's third law was, I think it was like 80 years before Newton's law of gravity, but Newton's law of gravity was ultimately created to explain this. It wasn't an apple, in case you didn't know that. Planck's law is actually another empirical expression. So this was kind of a relationship that was observed in data with a little bit of theory, and then quantum mechanics was partially created to explain things like this. But if I have this neural network, this large model that's trained on diverse data, and it's kind of, everything's kind of stuck in this neural network space, I can't really build theories that describe this, right? So this is kind of my problem. So I think one approach, and this is what I'm going to tell you about, I think one approach to kind of solving this difference is when we go from a high dimensional data set to a neural net, which is kind of like a compression. Is it getting feedback? I don't know. So this is kind of like a compression. So we go to neural net space. I'm going to tell you how to do the final step as a distillation. So kind of converting this neural net learned compression into theory, which is kind of, I think, one possible way we can efficiently use machine learning to kind of build up theory. Okay, so my key point that I'm going to try to convince you of in this presentation is neural nets trained on massive data sets, they can find new insights. So they can have new insights kind of buried in the weights that they've learned from kind of training on completely unrelated, so you think, data sets. The real challenge is kind of pulling out that insight and distilling, okay, what did it actually learn? And how can we use that to improve our scientific theories? So, okay, so I'm going to talk about interpretability. I'll tell you about this idea called symbolic regression. Talk about neural distillation. We'll go through a couple examples. Okay, so the traditional way of interpreting neural networks kind of involves feature importance. So say I have this image classifier and I look at, okay, what is the most sensitive part of the image? what is my classifier sensitive to? Maybe it's like the faces of the lions or the face of a dog. This is traditionally how you would do feature importance in computer vision or language. This is a fun example from a paper in 2016. This uses this interpretability technique called LIME. Essentially, you can try to interrogate the model and see what's important to it. So here's a dog playing the guitar, and so if you interrogate the probability for electric guitar, kind of highlights that part. Acoustic guitar, maybe it highlights that part, or Labrador kind of identifies that part. So this is kind of how you would do interpretability in computer vision NLP. But I think like in science, we already have a modeling language, and I think it's really important to exploit that. So computer vision, I don't really have a model for a dog or a cat. Like there's no mathematical model for a cat, but in science we do. We do have like a really strong framework for describing the universe, right? Mathematical equations. So if you look at like a cheat sheet of physics, you can see that there's so many different analytic expressions. They very accurately model our universe. So I think when we do interpretability for machine learning and science, we should really try to get explanations in this language rather than just feature importances. So for physical problems, one nice part about this is that when you interpret the model with symbolic expressions, you can often get better generalization performance than the original neural network you're kind of explaining. So I'll give some more examples of this, but this is kind of like an alternate inductive bias. So if you think about like when you train a neural network, there's kind of like this implicit prior over the space of functions it could take on, right? When you search over the space of analytic expressions, that's a different prior over the space of functions, and it seems to be really good for modeling the universe. And I think this is because the analytic operators that we're used to, they kind of have these geometrical properties. Like plus is like spatial translation, multiplication is like length to area to volume, and then you have a range of other operators that are kind of like solutions to different differential equations. So I think this is kind of it's a cool kind of inductive bias. It's more of like a functional inductive bias. So this brings me to this technique called symbolic regression. This is what I've worked on for the past few years. Essentially, it's a way of, it's a machine learning task where you search for analytic expressions that optimize some objective. Okay, so if I have this equation, y equals z plus 2 sine z, this would kind of be represented by this tree, and I would search over the space of trees until I find one that fits my data set. Okay, so rather than fitting parameters in some fixed model, you're searching over the space of trees while fitting those parameters. So the state-of-the-art approach to this is actually a genetic algorithm. There have been kind of like transformer-based approaches, but they don't win benchmarks yet. So genetic algorithms are actually state-of-the-art for this task. So for example, I might do a mutation on a tree, kind of like switch operators. And these are just ways of exploring this space of expressions, okay? You could also breed expressions. So maybe you have one symbolic expression that fits this part of the data set, another expression that fits this part of the data set. You might breed them together and kind of cross over. So these are all just ways of exploring this space. But what you're trying to do in symbolic regression is jointly optimize accuracy of the fit and minimize complexity. So complexity is very complex. It's a very complex subject, but essentially it's user defined. So you could think of like the number of nodes as the complexity of an expression. So symbolic regression is trying to optimize accuracy and complexity, okay? So there's a couple open source frameworks that I've worked on, Pyser and symbolicregression.jl. If you're interested, I encourage you to check them out. I think it's a really useful technique for kind of interpreting neural networks. I'll show you some examples of that. The way these codes work is it uses a technique called multi-population evolution. So essentially, if I have this population of expressions, so these are like different candidate expressions, they each fit the data in a different way. What I do is I randomly sample those. So I randomly sample maybe like 2 expressions. Of those, I compute the fitness. So maybe the fitness is like a combination of accuracy and complexity. I take the fittest and then I do a perturbation. So maybe I mutate it, maybe I algebraically simplify it, maybe I do a constant optimization. These are just ways of exploring the space. I take that perturb expression and I put it back in my population. Essentially, you just go through this loop enough times. Yeah.
I didn't want to interrupt.
Oh, yeah. Yeah, so you go through this loop enough times, and you'll eventually arrive at, you'll converge to a point in expression space. Yeah.
So this evolution is not using any language model. This is just like simple Python.
Yeah.
Okay.
So there are language model approaches. They work well if you know the space of expressions that you're searching, like you know maybe the ground truth, and you kind of put those in your training data set. But it's really hard to get general language model approaches to this. Yeah. It's another question. Yeah.
In this case, are you trying to fit the original data, or are you training a neural network, then trying to fit the neural network with the expression?
Yeah, second
Okay.
one. Yeah.
Got
Yeah.
it.
I'll show an example of that. Yeah. Okay. So the way you scale this, so this is all, I'm going to get back to neural networks. This is the interpretation strategy. So you can scale this up. So the way you scale this over many cores is you kind of have different populations of expressions living on different cores. You can kind of think of them as like islands of expressions, and they each go through evolution. Different islands will kind of specialize. So maybe one island is like polynomials, one island is exponentials. It's kind of like different species. Okay, they evolve independently, and the reason for this is you get a nice parallelism, right? You can evolve them on different cores. After a number of iterations, you have migration between these islands, and that's kind of how you do massive searches. Yes.
Sorry. So your procedure doesn't look inside the neural net at all. It just looks at the input output, is it?
Yeah. So I'll get back to that. Yeah.
Okay.
Yeah.
I'll ask one question too.
Yes.
I mean, it doesn't feel like this would make very good progress as a search procedure, because I mean, for some things like addition, it might be okay, but it sort of feels like if you're considering taking 2 expressions and multiplying them, that what comes out is not going to look anything like either of your component expressions before.
Oh, so, you mean the breeding itself?
Yeah, like it doesn't.
So it
doesn't feel like it's going to be very goal directed.
Yeah. So the simplest way to think of like how the breeding could help you is just think about feature importance. Say you have 100 variables. The most important variable is going to appear in more expressions. And so when you do the crossbreeding, you're more likely to have that variable put into your expression tree. Now, of course, it's much more complex than that, because you can have kind of atomic sub-expressions. So maybe the same sub-expression appears in many different trees, and maybe it appears in the same expression multiple times. It's kind of like a way of thinking about feature importance, the crossbreeding. Yeah, I mean, genetic algorithms kind of seem like there's not really any kind of it seems like a dumb idea, but it's the best idea we have, basically. Like it's so there's a yearly competition called Symbolic Regression Bench at Gecko. The winners are always genetic algorithms. Yeah. Unfortunately, yeah.
What competition is that?
SR Bench. Symbolic Regression Bench. Yeah. Okay. So I'll do a couple more slides on this, and we can get back to neural networks. So this is kind of how it looks when you're searching. So if I'm trying to fit this line, I do different perturbations. Maybe I mutate a node, coast assign, do a constant optimization, do more candidates. It's kind of like I'm MCMCing expression space. I spent way too long on this, so I'm going to replay it. Okay. Yeah, add a node. And these are all different, like I'm just exploring the space of expressions with evolution. Mutate. And there are some kind of MCTS approaches. So you can weight the probabilities based on the current expression. But so my code PySer just uses fixed probabilities. Okay, so what's this one? Oh yeah. Yeah, so there's a Python API. Okay, back to neural networks. So the point that I want to get across in this presentation is we can use this symbolic regression to distill a neural network into an equation, okay? And then we can get insight from that. And so the basic idea is that you train a neural network normally. So whatever the neural network is, you train it normally. After training, you freeze the parameters. You just stop training, freeze the parameters. Then you observe the latent spaces. So maybe I look at this latent space and I kind of record what goes in. I look at the output, so this other latent space, and I record the outputs. Once I have enough of those over my maybe training set, then I feed those into my symbolic regression code and I fit different expressions to it. Okay? That makes sense?
Do it with the original data set without doing the neural network?
Yeah, great question. So I'll get back to that. But yeah, that's a good question. Yeah. So the full idea is that you would do this at multiple parts of your network to kind of build up this hierarchy of symbolic expressions. So maybe I have two networks. Maybe this is like a graph network. This is my node update model. This is like my edge update model. What I would do is first fit this network and kind of replace it with expressions. And so I kind of replace the neural network with my symbolic expressions. Then I retrain my second network. And this just kind of helps pick up any errors in training the first network. And then I would replace my second network. And so now I've kind of completely replaced every part of my network with expressions, with symbolic expressions. And so this is ultimately more interpretable than just this massive neural network model, right? So the reason you would not just do direct symbolic regression is because of the combinatorial explosion. So if you were to search for this expression directly, you would have to consider many more symbolic expressions than if you consider this separately from this. So the scaling is going from n squared expressions to 2n expressions.
So is this because the dimensionalities of the intermediate states, or because you're saying, oh, sorry.
It's basically a way of factorizing the problem into sub-expressions.
But I guess what I'm wondering is like the space of functions that a single hidden layer neural network can represent is the same as the space of functions that a deep network can represent. So is it is just because of the input and output dimensionality, or is it just because it's actually simpler in practice, or something else?
So what you would normally have is some kind of inductive bias to eliminate the functional degeneracy. And you would, I guess you would assume that F is some complexity expression, and G, the second network, is the same complexity expression. And so rather than searching over all possible expressions of both networks combined, you would just do one at a time.
And you can't,
it's kind of like a student-teacher approach,
but you can't,
like parts of the network.
You can't provably say that this module has this amount of complexity. You just sort of assume it does because has fewer layers.
Pray to God that
Yeah.
it does. Yeah. if it's like more complicated than your expression, you're kind of screwed. So like one of the problems with this approach is you have to make a choice of what operators you're going to use to distill the network. You would usually choose those operators based on what would give you the best interpretation. So if it is if it's some problem in astrophysics, I would choose like plus minus multiplication, exponential, logarithm. But if I was in maybe particle physics, I would choose like dilogarithm and kind of operators common in that field. That makes sense. Yeah. Yes.
Yeah, so you gave some graphical examples before. It looked like interpolation. Is this a type, or method for achieving interpolation?
It's so okay. The basic idea is that when you train a neural network, you are implicitly assuming some prior over the space of functions. When you do this symbolic distillation, you're kind of transferring it to a different prior, so that when you go out of distribution, you get the second prior, you get the symbolic prior.
I'll open this later.
Yeah, okay. Yes.
I was wondering does this assume any restriction on the structure or topology of the neural net that has to kind of conform to the solution that you're looking for?
That's a good question. So no, so
Circular,
you would normally just choose a multi-layer, like a normal multi-layer perceptron. Like if you're doing like graph networks, you would not impose any kind of functional regularization. I mean, there's going to be an approximation error, right? Like you're not going to get a perfect approximation of the multi-layer perceptron because that would be an infinitely complex expression. You're trying to find a simple approximation of the behavior of that multi-layer perceptron. It's going to be an approximation though.
But it seems like, sorry.
Yeah, it seemed like in your previous slides, when you were showing this iterative process, you kind of knew what to fit to which part of the network, or maybe I'm misunderstanding that.
We're searching with a genetic algorithm over the space of expressions. We choose the operators. You have to make that choice. You have to choose the operators. You have to choose how you define complexity. Those are arbitrary decisions that you would base on your constraints. There's not really any, there's not really any like fundamental reason you would choose one operator.
So the ground truth, but is the expression, do you have a ground truth expression that you?
I mean, it depends on the problem. Like sometimes you're trying to rediscover something to show you can kind of reach human level performance, but other times you're actually discovering new scientific equations. In those cases, you would choose, maybe you would have, maybe you would kind of base it, okay, this field is usually described well with these operators. So I would kind of choose those operators in my search. But I mean, like you might just not know the operator.
Sure.
That would be best. So that could be like a different optimization problem, like learning the operator. Okay. So, so traditional approach, you have data, you try to describe it with a theory. In this kind of proposed idea, you would go from data to a neural network. So you kind of compress any patterns in that data set with a neural network, then you distill it to symbolic form. Okay. So I'll talk about some examples. So one of the first things we tried in this 2020 NeurIPS paper was graph neural networks. Graph neural networks are quite easy to interpret with this strategy because they have a similar functional form to force laws from classical physics. So what you do when you interpret a graph neural network, so say we're trying to predict the dynamics of like some interacting particles with a graph network, what we do is we encourage low dimensionality in the message passing space. And that gives us, it essentially forces the graph network to have few latent, it's basically like few equations. So I'll just show this video. So we start off, we generate simulations of particles. So this is a spring law. We try to model this with a graph network, graph neural network. Okay, so we try to predict these dynamics with a graph neural network. So these are the predictions in gray, and the ground truth is colored. So we do this with the graph neural network. We regularize them with L1, and this is essentially telling the graph network, I want you to find a simple model for me. Like I want to have few equations. And you can see here, it only finds two equations. There's two latent dimensions that it uses, and all the other ones are sparse. So what this essentially gives us is that when we try to fit symbolic regression to it, we get two equations that we replace the edge model with. And those happen to be the same as the spring law. So we've kind of shown that the message passing function in this graph network is the spring law. So, I mean, this is a rediscovery, but it's a test for this approach. Okay. Okay, so the next thing we did is knowledge discovery. Like the whole idea of this approach is that you want to find the scientific insights that deep learning is finding from data. So we're from an astrophysics background, so we have this dark matter simulation. We want to find new kind of laws that describe the clustering of dark matter. Okay. We have this graph neural network. We train it to predict the properties of dark matter based on kind of the surrounding particles, which tells you about the clustering of dark matter. So the neural network is able to beat traditional metrics for this, but we want to understand, okay, like what insight is it using that it's able to beat traditional metrics? Yeah.
Yeah, maybe this bread and butter in your field, but just how do you represent continuous matter with the graph?
Great question. So you would traditionally there's this approach called a halo finder. It basically draws balls around blobs of dark matter. Those become nodes in the graph.
Oh, dark matter is discrete.
No, so dark matter.
Blobs of,
yeah, like the simulation kind of represents it continuously, but you would do a search kind of for clusters of dark matter. Those clusters become nodes in the graph. And the nodes would have properties like this is the mass of this cluster, this is the radius, things like that. So that's how you discretize the simulation into a graph. The edges are just based on locality. You would just do a radius cut.
So if you can simulate it, are you not using some physical laws like gravitational laws to simulate it already? So
yes.
Are you learning something more than what you're putting into the simulation?
We're learning a summary statistic for kind of how it clusters. But the ground truth physics is known because we're simulating it. Like it's just gravity, right? We're learning how the mass is clustered.
So we're
like what's a good law for clustering it?
Got it, but we're not
It's
learning
an
any properties of
effective physics, basically.
I see.
Effective law.
So basically, some emergent properties from the gravitational laws that is coming up. We are learning better representations for the emergent properties that are coming from gravitational laws.
Yeah, it's basically learning a law that describes the emergent properties in the simulation. Okay. So we apply the same approach that we used to get the spring laws, and we get this dark matter over density equation. It basically predicts properties of the dark matter based on a summation of the neighbors. So I'm not going to describe this because it's a different field, but it's basically like a new equation. So this equation was not known before, and the graph neural network found it, and then we distilled it with symbolic regression. So it kind of describes the clustering of the dark matter. Okay, so I'll show a second example. So this one's more classical. We wanted to see, can we find Newton's law of gravity from the solar system dynamics? Okay, so unknown masses, unknown dynamical model. We literally just fit the solar system with a graph neural network, try to predict the next step of every planet. So this was led by Pablo Lemos at Mila. So it basically looks like this. The wireframes are the predictions. The colored planets are the ground truth. This is another video that took us way too long to make, and I regret doing it. And you can see, so the original graph network, like, it doesn't quite pick up all the dynamics. It kind of looks like it, but it doesn't pick up everything. Yeah.
Yeah, not to take away anything from it, but
wouldn't you want to do this with what was known at the time about the dynamics, in terms of the observations of?
Yeah, so, okay, I think I see what you're saying. So you would say, like, why not give it like a 2D sky map? Is that what you're asking?
No, okay, I guess what I was asking is what's the input? Is the input?
So the input is
we know
give
about the orbits right now today?
No, so we give it as input 3D positions of every planet, and then I think it's like 20 moons over time.
Right.
So give it the precise 3D position.
Exactly.
We don't give it the masses. We don't give it any orbital parameters.
Yes.
Just give it the raw physical coordinates. Is that good?
I think for now, yes.
Okay, for now.
Did you use GPT-4 to do the?
Okay, so we train this network. It's not perfect, so we want to use this new interpretability technique and understand what are the latent spaces actually doing? Like, what are they actually computing? We stick it into PySir, and we get these equations out. So this axis is complexity, and this is essentially like, I mean, I should have done accuracy. It's an accuracy complexity trade-off. Basically says like, this is a good bang for your buck. Okay, the simplest expression, x over r, we get x over r plus a constant. We keep adding complexity, and we get to this expression, which is Newton's law. So mass times x over r cubed. So it's basically like the x component of the force. There was actually another expression. So this fits the latent space better. It's basically Newton's law of gravity plus a constant. And we realized like that's just the degeneracy in the network. Like it's basically learning its own modified law of gravity that works because it knows how to invert it. But you can see the complexity trade-off is just not worth it. So we prefer this one, which of course happens to be the ground truth, Newton's law. Okay, so we take this law, we take this symbolic expression, replace the neural network, and we roll it out again. And we see like, okay, how well does it do? And so, yeah, it looks better. I mean, it's not perfect. Like this is Mercury. Mercury's prediction is still off. Okay, so we try to figure out, okay, like why isn't it perfect? This is Newton's law of gravity, like it should be perfect. So I mentioned earlier that we're letting the network learn mass values for every planet. We don't give that as prior information. It has to learn the masses. And a lot of the masses are just completely off. So the predictions are in red, and the multiple dots is basically different trials. You can see like Earth is like way under predicted by like 100 times. Mars is way under predicted. Some of the biggest planets it gets, because I think, yeah, those are just easier to predict. But we realize like, okay, this network it's essentially learning a modified law of gravity that works for the network, and it's learning mass values that work with that law. Okay, so what we did is we have this law of gravity, we retrain the masses. So we re-optimize the masses to work with that symbolic distillation, which is like, remember, we're like the original masses that it learned were optimized for the full neural network, not the symbolic expression. Okay, it's not a perfect approximation of the network. It's kind of learned this modified theory of gravity. So we re-optimize the mass parameters, and then it's good, and then it gets it correctly. You can see all the predictions are good again. Okay. So yeah, I mean, all the predictions are good. A couple are weird, like this is the moon Hyperion, like over predicts the masses. I think it's just because we had like some moons missing from the data set. So we're not worried about that. Okay, third example, this is my final example. So a lot of what I talked about is about interpretability. So converting to analytic expressions for interpretation. Another cool thing you can do is when you translate it to a symbolic expression, you can do it for speed. So this is a paper led by a grad student at Wisconsin, and they use symbolic regression to optimize the speed of a neural network. So you take the inputs and outputs of a neural network, and you try to find the fastest possible expression on an FPGA that approximates that neural network. And so rather than searching for complexity, you're searching for number of clock cycles on the FPGA. So it's like completely different objective, but it's the same kind of idea. You're trying to distill it to a symbolic expression. So they approximate a neural network with 90% accuracy. So you can get pretty good predictions. And it's 5 nanosecond inference time. So their application is the Large Hadron Collider for kind of detecting anomalous particles. And so rather than needing to have this massive neural network, you can distill it to this ultra fast FPGA code with this idea. You get really fast prediction. Yeah, and I think I'll stop there. So I have this web page of like other examples of this. I think so. Yeah, the things I'm interested in discussing are, is a pure neural network approach to AI for science possible? Like if we just keep training larger and larger models, would we ever expect to get the same level of generalization compared to theory? So like, so Einstein's general relativity was derived from only a few ideas, but it can predict things like black holes, right? Like obviously he didn't observe a black hole, he just derived it. So is it hopeless to kind of expect that level of generalization from foundation models? Or do we need to kind of have this mix of distilling them to theory? And then, yeah, another thing I'm interested in is like, how do we distill very large models, like language models, into scientific insights? Like, can we use this idea, or do we have to take other approaches? Yeah. Okay, I'll stop there. Thanks for coming. Thanks for having me.
Okay, still time for more questions.
I guess I could follow up on my previous question. I think you alluded to it here in terms of general relativity, etc. So I was getting at the same point with respect to gravity, in the sense that when the law was formulated, I'm assuming that there weren't, 3D coordinates for all the planets over time and so on. So so the predictions are done with extremely small amounts of data, and so is this a dual view where there's of science where there's lots of data and you use neural nets and then derive, or can you discuss a little more about where this would be applicable?
So I don't quite follow the question. Is the question about specifically Newton's law of gravity?
No, well, it was sort of saying, look, there seems to be, okay, so my first reaction to the derivation of Newton's law was, oh, that's really remarkable, right? It's but then I thought, well, but it's using much more information than
I see,
than was used historically.
Yeah.
And so if you're saying, well, this is a way to get at science, it's in a different domain, perhaps. So can you discuss a little bit about that?
Yeah, so the network is not at the level of Newton. I'll say that. Like it's a simple neural network. So I think there's a lot more work to be done. So we also had to put in, so I didn't mention this, but we had to put in another few inductive biases in the network to actually get that performance on that data set. So it is a lot of data. So we gave it 30 years of dynamics data, but actually it's only, I think there was only 30 bodies. So like planets and moons and the sun. It's just not a lot of data for neural networks. Like you only have 30 examples. It's really hard for the neural network to pick up a general principle. And I think that's why it kind of learned this modified theory. So I think, like, I ultimately think we just need better ways to impose simplicity priors on latent spaces in neural networks. Kind of like symbolic simplicity. Like I would love some kind of way to impose that parts of a neural network learn a symbolically simple model. But it seems hard to do that. But yeah, I think we need to eliminate. So we had rotation equivariance was another inductive bias that we put in, but we didn't need to necessarily. So there's a few other priors that we want to remove and still recover that result.
Can we take Becky at this?
Yeah, so you may have actually answered my earlier question about interpolation. and Einstein's prerogative on general relativity. Mercury's perihelion was part of his historical motivation for that pursuit.
Yep.
I'm assuming you knew that, like, getting into this. So, like, when you come up with like better matching with Mercury's orbit as an elliptical orbit, does this basically imply that you are demonstrating elliptic curve interpolation?
Regarding the precession of Mercury, so I think there's just like it barely learned Newton's law of gravity because you only have 31 different masses you're training this neural network on. I think it's just not enough data to kind of fit the neural network, and like it barely found Newton's law of gravity. I don't think it would have found general relativity unless we gave it a lot more data.
Well, I mean,
or we gave it like different principles.
Yeah, well, Einstein didn't say from like Mercury's orbit that he like was corroborating everything about like his concept of general relativity. It was motivation and like reinforcement to do further work. So I'm not saying like, you know, QED, that's what you should expect.
Yeah, I think like,
you know, like, did you demonstrate in the way that you got really close to Mercury's orbit from data that you were effectively demonstrating elliptic curve interpolation?
Yeah, definitely. Yeah, I think like generally it's interesting to think about how you would impose other priors. So like Einstein had other things to work with, obviously, not just dynamics data. And I think that is something I'm very excited about language models for, is you can provide like very flexible data representations into the model.
So I have a question about, like, on a high level, why do we expect scientific principles to be simple? And like that seems to be having some kind of reductionist assumption about science, while there are a lot of complex systems that might be like not very well explained by these kind of rigid symbolic expression.
So I don't think science is simple. I think when we talk about simplicity, we talk about it in terms of like simple in the basis of my existing ideas. So if you think about like plus, like adding numbers, that is a very abstract idea. Like the fact that we consider like adding two numbers to be simple, that's just because we've learned it and it's become so familiar to us. But it's not like we have a register for adding numbers in our brains that like these are very abstract concepts. And I think when we talk about simplicity, you should have like a very clear objective. So interpretation, you should think about how would this insight kind of give me the most, I don't know, like how would it be most interpretable to me, and kind of choose how you measure complexity in that way. Or you could think about like the FPGA example, like complexity is the number of clock cycles to compute this thing. And so that's like a completely different objective. But there's definitely not a universal definition of complexity. Like it's kind of like it's hard to define. It's ultimately like a philosophical black hole to think about this. Yeah.
So I have a question going back to something that Umesh was bringing up. If you said that you have very little data with 30 objects for 30 years. If but back then they had like what 10 objects or something that they could actually track that was kind of planetary type things that So if you had that for like 10 years or something, your neural net would still train. It would still train to very low loss, right? But you're saying it would learn something wrong. But you could still do what you did, and you extract a simple symbolic expression that comes out of it. It would presumably still be simple and fit well, but be wrong. It'd be really cool to see what that would have been, what that would have looked like.
Yeah, I think so too. So the way it actually happened was so Kepler fit his law, and then so Newton's gravity was to kind of explain that rather than the raw data. Like here, it's different in that we're fitting Newton's law of gravity directly to the raw data, which is a bit different historically.
So going back to the idea of an AI scientist, what was interesting to me is that if you have this methodology, it would presumably presume simple looking things that could be wrong.
I mean, it was wrong Like Newton's law of gravity is wrong, but it's
Mostly right.
mostly right. Yeah.
This would be stuff that is wrong, totally wrong.
Yeah, it's a good approximation, and it's yeah.
Thank you. Quick question about this. Did you try this on the Lorentzian dynamics?
No.
Like, I mean, would it learn the Lorentz attractor? It's a very simple system, but it's extremely chaotic.
Yeah,
right?
I mean, it depends. Like a lot of it depends on how you set up your network and how you impose specific inductive biases. So if you're learning a dynamical model, you would probably want to do like a neural differential equation and kind of learn an update rule and then fit symbolic equations to that. But if you just like fed in a JSON file of dynamics to a language model, it would be much harder to interpret.
I mean, but I'm wondering, like, it's not that different from a planetary system, right? Like you have positions. There is finally a dynamic. I mean, it's finally a physical.
Yeah, like if you set up the inductive bias correctly, it would be. I think it would be easy to find that law.
Okay.
Yeah.
It would be great to see, but surprising.
If I intersperse one question, I'm sorry, can I come back to this issue of how much you need the neural net? I mean, if I understood correctly, the answer you gave was, oh, look, maybe you've got a neural net that's a composition of two parts.
FAQ slide.
And okay, and therefore I'll be able to do a symbolic expression for each half.
Yeah.
But it seems like the extent that that's a win for you, you're exploiting prior human knowledge of the domain, because that's presumably why the human being designed the net like that, unless you were doing some kind of neural net structure induction separately.
I see.
And I mean, it sort of seems like, it also seems like that kind of composing from parts is only limitedly useful, because, right, if you did too much of that, you'd kill your goal, right? You know, like if the neural net was something like even like a 2-layer transformer, and I said, well, let me learn a symbolic expression for each cell in the mid layer and then another cell for what's computed at the top layer. Right. Well, something would come out of the symbolic regression, but it'd be so complex that no one would want to look at it anymore, right?
Yeah, definitely.
Yeah, so.
Yeah, okay, so it's like, why would you not fit directly? So ultimately, like neural networks, maybe, okay, so for our problems, you require like 1 million steps, like 1 million gradient descent steps. Genetic algorithm, to fit that complexity, you have to do 1 billion evaluations, because genetic algorithms are much less efficient. You don't have gradients, right? There's some approaches that uses gradients, but they're not as good as genetic algorithms. So it's much easier to train a neural network on the raw data and then do like a student teacher with the genetic algorithm, because then you only have to fit the inputs outputs of, say, the neural network. So it's just mean squared error, and it's much more efficient than having to do this like multi-step kind of aggregation in the neural network. So that's one reason. Yeah. The other reason is the factorization. Like training the neural network first, we'll kind of factorize it into sub-expressions. So you do need to have some kind of knowledge, some prior knowledge about how that structure should work. I mean, you could also like learn it as you suggested. Maybe, so in our example, we impose that the pooling is a sum, but maybe you could have like different pooling and then kind of sparsify it so it picks one of them. But it is kind of something you have to impose. I mean, like if you if you try to do this symbolic distillation and it just doesn't work well, you've chosen the wrong inductive bias. I mean, I think that's like a good general way to tell if you've chosen the wrong inductive bias or not. Luckily, in a lot of physics problems, we do have, like if we don't know the specific law, we do have good inductive biases, because we know like causality cannot be violated. There's different symmetries that have to be enforced because we know energy conservation or whatever exists. So there, like in science, I think there's a lot of inductive biases that you can exploit.
Maybe a little more philosophical, but you opened the talk by saying, quote, "I want to build an AI scientist."
Yeah.
This clearly seems like one piece of a bigger puzzle in that respect, and I'm kind of curious what the rest of the picture looks like.
Yeah, I mean, yeah, that's a great question. So I think, I mean, it's more kind of like a call to action. Like I wish more people would work on just automating scientific research, like in the natural sciences. So this is kind of the model discovery aspect. It's not even the theory development aspect. It's like going from data to empirical equation. But we still need to kind of have some way of building up theories that give you that empirical relation. We need to have experiment design methods. And I really don't have a good handle on how the whole picture would look. But we do ultimately need that whole loop to actually automate science. Yeah. So yeah, I mean, there's a lot of work to do. It's yeah.
Well, it seems like we're about to come to the end of the questions, and it is 3 o'clock when coffee is meant to start again. So thanks a lot, Miles.
Thanks. No.
The only two. I know.